Okay. So when you do molecular docking, right, you are trying to see if your drug is going to bind to your protein. When you take your medication, be it your Tylenol, be it your ibuprofen or whatever, it's not going to your body to perform magic. No. What it's going to do there is to look for its target. What is the cause of the headache? What is the cause of the body pain, right? So whatever is the cause, it could be an enzyme, it could be a receptor, it could be an ion channel, right? What it's going to do is to bind to that target and exert a conformational changes that will result in your headache or pain going away, right? So that's what it's doing. So when you are developing a drug for a particular target in drug discovery, you are looking what you are trying to do is you are looking for a drug molecule that can bind conveniently to your target, right? And inhibit the target so that maybe it's the headache that you're having can disappear, or the body pain that you're having can disappear, or maybe you are sneezing or you are allergic to something. So your drug binds to whatever that is the cause of the problem, either inhibit or activate the cause of the problem so that your symptoms can vanish, right? So that is exactly what happened. So when you are developing drug, you are concerned about a drug that can bind to that target and be able to cure whatever symptoms that you are experiencing. That is how drugs work, right? So, like Dr. Scott taught you last time, docking is a way of finding a drug that can bind at the active site of a target to see whether they are going to exert therapeutic effect or not. So there are different ways of doing docking. You can use Chimera. So Chimera can dock for you, but you can only do one drug at a time or one molecule at a time. But there are instances whereby you want to try maybe like 1 million compounds, or you want to try 1,000 compounds. So on the average, you can spend like, let's say like 10 minutes on Chimera on one molecule. So imagine you doing multiply 10 minutes by 1,000 if you are working on 1,000 molecules, right? But alternatively, there's a way you can do your docking and you can dock all the 1,000 or 1 million compounds at the active site of your molecule. And you just have to do it, leave it, and you can do something else. And the docking will automatically go by itself. It's going to be an automated process, right? And that's what I want to show to you today. And there are different ways you can do it, right? You can do it using AutoDock on any command line, and you can as well do it using this Pyrx software. So Pyrx software is just a simple software. So let me quickly show you how to download that and install and download and install. Just type download Pyrx, 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 right? Just click on that. Yes. So I don't know if they have, Scott, do you know if they have window distribution? Sorry, iOS. I know they have, yeah, they have, yes. So if you are using Windows, you can download the Windows distribution. If you're using Linux, you can download Linux. If your laptop is Mac, you can download the Mac distribution. Just download that and do your normal or regular. It's just a normal way of installing software on your laptop. And that's all. Okay, do we get that? So once you do that, you can install, double click, and it's going to give you it may not be in the same arrangement like my own. I have to make my own arrangement different. So, but it's still going to be the same basic. You are going to see your file, your Vina wizard. You are going to see your molecule, Autodoc, this, and you are going to see the 3D screen. You are going to see the 3D screen, right? That's how it's going to do. So it can display for you in different way, but these are the basic workspace that you are going to see. So that's fine. So that is the environment of the software, right? So what do we do next? We are trying to develop a drug, right? So let's come up with, a drug. Let's see with a protein. Let's work with SARS and a human ACE2. Human ACE2 protein, I think I've mentioned in the past, is the receptor in human body that accepts SARS-CoV-2 virus, right? So it's the receptor that accepts SARS-CoV-2 virus. So if you want to stop COVID from getting to the body, you can develop a small molecule, a drug, that can bind, right, to SARS-CoV, to the ACE2. And once it binds, it can stop COVID from binding, right? So let's assume that's what we want to do. As we are here, we want to develop a drug that can bind to the ACE2, right? And once it binds to the ACE2, it can stop SARS-CoV-2 from what? From binding. So such a drug should be able to bind very well with ACE2, right? So the first thing in molecular docking is two things are involved. Number one, your protein. Number two, your set of drugs you are working with. So let's first of all go and let's download our protein. To download protein, I think Dr. Scott will have mentioned that last week. In your last classes, you go to what is called protein data bank. So this is a data bank where they deposit protein structure all over the world. All over the world. Just type protein data bank. I think protein data bank is being sponsored by the US, by NIH. Protein data bank. Yes, it's called RCSB PDB. Protein data bank. This is how it looks like. This is how it looks like. Protein data bank, right? So the first thing is to download your what? Your target. So our target in this case is going to be angiotensin converting enzyme 2. Enzyme 2. This angiotensin converting enzyme 2 is a good enzyme in the body that helps in regulation of blood pressure and some other functions, right? So this is protein data bank. So the first thing we do here is to download. You type your protein. You can type any protein. If you are looking for glucose kinase, if you are looking for hemoglobin, you are looking for structure of insulin, you are looking for exopeptidase and angiotensin converting enzyme 2, you are looking for, let's say, HIV protease enzyme, any protein, any enzyme that you have come across, you want to study them, you can type them. So let's type human. So one thing here is, don't forget, most of the enzyme in our body is also present in other organisms. So I always encourage people, when you are looking for a particular protein, try to put the organism. So like if I'm looking for a protease enzyme, there's protease enzyme, there's protease from SARS-CoV-2, there's protease from Ebola virus, there's protease from other organisms. So for you to make sure you are doing the right thing, you have to put the name of the organism. So if I'm looking for ACE2, angiotensin converting enzyme 2, there's angiotensin converting enzyme 2 from dog, from monkey, from rabbit, from mouse, from mice, right? But to be sure that I'm doing the right one, I have to put human angiotensin, or if you know the short name, converting enzyme 2. Human is 2, or you can put is 2. So it's loading, searching the database for us. Yes. So this one, so if you look at this, so it's going to give you multiple. So you have to look at this.
Sorry, Dr. Do you want us to be following along with you doing this?
What do you say?
Did you want me to be like, did you want us to be like going along with you, or did you want us to just pay attention?
Whichever one is convenient for you. If that is not going to stop you from listening, fine. But if it's going to stop you from listening, you may not. I will still make this video available for everybody. So I think because the video will be available for everybody, I will probably prefer you to listen and watch. Yeah, the video will be available for everybody to watch. So even though I put human, right, it still give me some. If you look at this, it's telling me the release year. It was released 2003, July 20. But the organism is what? Drosophila. So this is not the one. I'm not looking for Drosophila. I'm looking for Homo sapien. Human is Homo sapien. If you go to the next one, it's also Drosophila. Now, if you look at this one, this is ACE2 targeting monoclonal antibody as potent this. This is from where? Homo sapien. That's from human. And this was released 2022, June 2020, June 22, 2022. So this could be a good one for us. So let's click on, let's go down first and see if there's another one. This one has antibody attached to it. So let's go down and see if there's anyone that has no antibody that is from human. That is from human. This is not human. Let's see. This also have antibody attached to it also. This is also failure. So let's go to the first one that we see that has antibody. So if we can still delete that. So let's go back to this. I think I'm not going to rush this because this thing can be tricky. So let's go back to the H2 that is human. Okay, let's take this. So you can click on this and explore the structure. Structure. So can you see? So this is H2 and some other thing attached to it. So now let's go back here. So if you look at the information here saying membrane protein, yes, it's a membrane protein. It's always on the membrane of the cell. So it is from there that it accepts molecules into the what? Into the cell. Organism is from human, Homo sapien. Expression, it was expressed in human. Is there any mutation? No. So we are not doing any mutational study. If you are doing mutational study, then you can be looking for mutation. Yes. That's fine. So let's go down. So it says there are, don't forget, if you look at this, what we have here, it says, if you look at it, it says H2 binded to BOAT complex, open conformation. Conformation, right? So it means it is not only H2 that is here. So we have to know which one is H2, and whichever one that is not H2, we do what? We delete it by the time we download it. So let's scroll down. Let's scroll down. So if you look at this, A and C is a transporter. So chain A, chain C is not the H2. It's sodium dependent neutral amino acid. So we are going to delete A and C. Chain A and C is not a H2. So let's go back there. So now if you look at this now, this is angiotensin converting enzyme 2. This is the one that we are looking. So there is 2. We have B and D. So we only need to work with one. So we can just take D, B, and delete D. So we are going to delete D and this A and C because that's not what we are looking for. So let's go again. Is there any other molecule attached to it? Any other structure? So what you are doing now is you are just trying to prepare our protein. You have to prepare your protein before you do your docking. So two things. The first thing, prepare your protein, right? And prepare your ligand. So what I'm doing now is preparing my what? My protein. So just downloading the protein first. So let's continue. Right. So let's go there now and let's download it. So we need to download this structure. So go to download file. Right. So go to PDB format. Can click on the PDB format. It automatically download for me. Right. So let me try to create a folder here. Let me call it. What's the name of this hour? Let me call it DOE class. Right. So let me copy it there. So I copy it into the DOE. Right. Okay.
It's like we're having some technical difficulties. What's going on? I just lost my electricity a few minutes ago, too. There's no hurricane. All right. He'll be back on soon. Just hold tight.
Hello, guys. Sorry about that. The electricity cut off in my office. Yeah, let me quickly share this again. Okay. All right. Can you guys can you hear me?
Yeah.
Okay, all right. So what you are trying to do is before we go to the docking, we have to get our target. So in this example, we are using human ACE2 as our target. So that's the first process, right? And we have successfully downloaded the ACE2 protein, right? So this is the protein, right? That's fine. Now, the next thing is, don't forget we have downloaded the structure. So, and from what we see on this, it is not only ACE2 that is here. We have to remove every other molecules that are there. So you can use another software called Chimera. So you can open that structure from using Chimera, right? So let's go to what you downloaded. So if you are not used to Chimera, this is Chimera. Just open it. Right. Go to. Let me go to where I have it. I have it in download the class and open. Yes. So can you see what you downloaded? This is the structure of ACE2 bounded to the sodium transporter protein, neutral protein. So if you remember, we said, can you see the chain A, B, C, D? Let me go back to Can you see? AC is sodium dependent neutral amino transporter. Only B and D are what? Are H2. And we said we only need one H2, so we can delete the main H2 and the other structures. Let's go back. So to do that, go to on Chimera, select. I think I'm going to show you how to download Chimera as well. Select. So we don't want chain A. Click on chain A. See, it highlighted chain A. Let me go back. So to delete, go to action, atom, delete. So let's go back again. Select, chain C is delete. Go back again. So these are the H2 that we have here. These are the human H2 that we have here. So we only need one. We don't need the two. So let's go back. So let's keep B and let's delete D. So go back to action again. Action, atom bond, then delete. So now we now have one what? H2. One H2. So it is in the open conformation. One H2. Actually, H2 has a zinc in it. So there should be the H2 is a metalloenzyme that has zinc in it. So let's go back and look for the one that has zinc. So another thing I want to say is this: you have to have understanding of your target. Yes. For H2, H2 has what is called zinc metal at the active site. So the one I have now doesn't show zinc. So we are not going to use it. We have to go, let's go and look for the one that has zinc. H2 bonded with zinc. So let's go back and look for H2 bounded with zinc. This is giving us something nice. So let's go back. Human H2. Okay, this is one. Let's try this. This is human H2. Okay. So this is structure of spike this is spike from SARS-CoV-2 complex with bat H2. No, we don't want bat. We want human. You see, those are the things that you have to consider. We want human. We don't want bat. So this is one of the undos that you have by you get. If you can get this correctly, you are on the right path. So getting the right protein is one of the first challenges you are going to face on the data bank. This is dog H2. This one is dog H2. And what that type? Let me put human H2. The structure of H2 from one organism to another organism may look the same, but they are not 100% the same. They are different in their structures to some extent. You know, I don't want to use a PDB code that I know already. I just want to show you how to search for this. Let's try to do spike RBD bound to H2. And that can give us a good. Okay, let's try this. So human, okay. Let's go. This spike, yeah, the spike is ABC. Okay. This does not have a stool at all. This has no H2. So let's go back. I don't want dog H2. I want human H2. So you have to, that's one of the things you have to look out for. They are giving us the one that has dog H2. We don't want. We want human H2. So square of SARS-CoV-2 in complex with this. Let's see, does it want this one as these are the things you pass through before you for you to be able to get. This is not H2 as well. So you have to keep looking until you find the one that has your target. This one is H2, but it's not human H2. This is mink H2. That's mink H2. You have to look for the one that has human H2. Okay, this is one with human with H2. Let's see if it is human H2. Okay, this one is human. I want to see if it has the zinc residues. So let's check if it has the zinc residues. I think most of them don't usually come with zinc residues because they didn't usually pick the zinc residues. Okay, that's fine. Let's go back to what we have, the one we have been using. So let's use this one. So this is what human. This is human H2, right? So this is what spike protein binds to before it can gain access to human body. Yes, this is what it binds to. Now, once you identify your protein, the next thing is to ask yourself, where is the active site of that protein? That's the next question, because that is where you are going to dock. You don't just dock on anywhere on the protein. You have to identify the active site of the protein and dock your ligand to it. So for H2, the active site of H2 is here. This is the exopeptidase site of H2 here, right? So that is, so we know, so this is, let's put it around the residues 518, right? Okay, let's finish that. Now this is done. Now let's save this. Don't forget we have deleted, so we have to save it. So let's save it as you save it as PDB. Save as PDB, and let's give it a name. We can call it, it's already prepared. Let's say prep H2. Prepared H2. So we save it now. So let's go back to, let's open Pyrx now. Pyrx. So we have identified our biological target. We have gotten the one, and we have removed every other thing that is not part of it. We remove it away, right? So what do we do next? So let's go here. So now let's go to Pyrx now and import our macromolecule. Go to File, click on Load Molecule. Load the molecule. So you go to wherever you have it. So I have saved in Download in DOE class, and this is it. Open. Can you see? Can you see it here? From File here, it's now here. Molecule, and you can see the structure, right? So that is the structure. So that's fine. So we have import our protein structure to Pyrx, where we are going to do the docking. So what do we do next now? The next thing that we do is what are the drugs that what are the compounds or drugs that we want to test? So can someone suggest for us? Let's go and download the structure, some drugs. So let's go to you can design your you can build your own structure. Let's go to PubChem. I think I will only stop on I will only stop on this. I don't want to bug you with. So this is PubChem. You can design your own drug yourself. That's one approach. So you can say, okay, let's design another a drug. Let's call it Javicin. Let's use from Javidiva, or any name. So you can design your own drugs, right? Let's say you are designing a drug, right? And you just put something, right? And you just put some, let's say you put some functional group, right? And you put maybe a carboxylic group on it. So you can design your own drug. So you can call this and mensomano, whatever name you want to give it, for instance, right? I'm just kidding, right? You can give it whatever name. So you can design your own drug and say, oh, this is the drug I'm designing. I want to see if that drug is going to bind with what with H2 or whatever target you are working with. So that's one. But let us do that to don't let us design. Let's go to let's suggest. Can anybody suggest a drug for us? Can anyone suggest a drug for us? So let's do chloroquine. Chloroquine. Let's try chloroquine. So chloroquine. Okay. So let's try chloroquine, for instance. So this is chloroquine, right? So this is for the docking, we need the 3D structure. Just click on the 3D structure, right? And download it. Go to download, right? Click on this SDF, right? It is what? It is saved. So let's go back and let's name it chloroquine. We name chloroquine. So let's put it in the folder that we had, the DOE. So let's have another let's try like 5 drugs or 4. Let's try like 4 drugs. So let's try another drug. Can anybody give us another drug? Let's say Tylenol. Tylenol, right? Click on the structure of Tylenol. So let's get the 3D structure also. Click on download coordinate. So let's go and address. Let's rename it to Tylenol. Let's put it also in this folder. Let's try one more drug again. Let's try one more drug again. Any suggestion of let's try ibuprofen? Is it ibuprofen or ibuprofen? I think my spelling is wrong. Is it ibuprofen? Okay. Let's try erythromycin, for instance. Erythromycin is a big structure. Oh, let's look for another one that has 3D. Let's look for another that has 3D. Let's try aspirin. Aspirin. Okay, aspirin has 3D. So let's download it. So let's go and change it. So let's just stop on this. aspirin. All right, let's copy it there. So now if you go there now, so can you see we have 3 drugs, aspirin, chloroquine, and Tylenol, right? So let me see, let's go back to Pyrx. Then from Pyrx again, you go back to your file, load, just the way you load. Now another problem here is it's downloaded at SDF, but what is it? Pyrx is not going to work with SDF. Pyrx prefer to work with mol2. So how do we convert that to mol2? You can make use of your Chimera, right? Let's close this. So let's go to Chimera, click open. So let's click aspirin first, open aspirin. This is the structure of aspirin. So you can, let's save it now as mol2. So that mol2, am I in that folder? Yes, in the folder. So aspirin. So it's going to save it as what? Mol2. Save. Close session. So let's do the same thing for others. Chloroquine. Save as mol2. So it's going to save it as chloroquine. Mol2. So close it again. Open Tylenol. Save as mol2. Yeah, so we've converted it to mol2. So let's go back to Pyrx. So let's say let's load now. Load molecule now. Load molecule. So can you see that now? So let's load it one by one. Aspirin. You have to do it one by one. Open. Can you see aspirin there now? Can you see the structure here of aspirin? So let's go back again. Load molecule again. Chloroquine. Chloroquine 2 is there now. Load Tylenol. So everything is there now. We now have everything. So we have our protein, aspirin, chloroquine, and Tylenol, right? That's what we have. Let me try to reduce this. Yeah, so that you can see this very well. So this is where the drugs are. This is the protein that we want to dock. Can you see? We want to dock it too. Now, that's fine. So once this is done, we are good to go, right? So, excuse me, but the next thing is, how will this software know which one is the protein, which one is the ligand? We have to specify. So to do that, go to this protein, right click on it, right? Go to autodock. So this is our protein. We are going to choose make it macromolecule. That's our biological target, macromolecule. Click it. It will automatically identify and set it and change it to PDBQT. And if you remember, what Dr. Scott was explaining to you last time has to work in PDBQT. So this one too will automatically convert to PDBQT, but you won't see it now. So now let's go to our ligand now. The same thing, right click, autodock vena, but now it is ligand. It's not going to be, our drug is going to be ligand, not macromolecule. Make macromolecule. Let's do the same thing for chloroquine. Sorry, make ligand. Tylenol, make ligand. So if you have 100 of compounds, you have to do make ligand. There are some other softwares that can automatically, without doing one by one, that can convert everything to, what is it, to PDBQT for you without doing this one by one. So now we are good to go. So how far have we, so so we have set our ligand and macromolecule. So click on this autodock vena, right? Now, this autodock vena will show you all that you have. Now, in my previous work that I've done in the past, I've worked with all this ligand 1, L1 to L up to this place, up to STD7, right? So is that one has been studied already. I'm not going, I can delete it, but I don't need to, I don't want to delete it because I'm still working on this one. So what you need to do now is, I'm not doing my docking on all of them. So you can specify. So I only want to dock on aspirin, click on aspirin, click on control, chloroquine, and Telenol. So I only want, if I want everything, I will just click shift and choose everything. But no, I'm not doing that. I only want aspirin, control, chloroquine. I'm putting my hand on control, Telenol. So those are the three I want to dock. So if you come to this side too, I'm working on this particular protein in the past. That's not what I want to do. I only want to work on the prepare H2. So once that is done, I'm trying to show. So once that is done, so we have identified our ligand, we've identified our protein, right? So you see a button here, click start. Click on start. So if you look at this, it's telling you that I've selected 3 ligands, and I want to work on this directory in prep H2, right? That's good. So once that is done, click forward. Now, this is where we are going. This is the last undos in this. So when Dr. Scott was showing you orthodox vena last time, you have to create what is called a grid box. The grid box is to specify where like I said, the active side of the protein is not the drug are not bind anywhere. It has to bind at the active side of the protein, right? And from your prior reading, you will have known the active side of your protein, right? So I have to set this thing now to the active side of this protein, right? And how do you know? It may be difficult for you to know the active side of this protein. And let me go back to camera and show you something. Right, this is our protein, right? And I told you from literature understanding that I know, the exopeptidase site of H2 is here, is at this opening, right? So let's say anything from 518. So iron, because this is where the zinc residues is, 518. So let's say residues 518. Let's go back. So how do we recognize residues 518 here? It's difficult, right? You don't need to stress yourself. Just come back to molecule, right? Then go to, this is the protein. Click on this plus. It's going to show you all the residues from 21 to the last. So let's look for 518. For instance, 518 here. 518. So we know where 518 is, the 518. This is 518. So you can right click on 518, go to display, label, atom. Can you see? It automatically shows me 518. So this is the residues of 518. So definitely we can create our grid box around 518. So now it's not left to you. How big do you want it to be? So you must understand the size of your protein. That's another thing you must understand. You must understand the size of the protein. Look at this now. So let's assume this is the active site. We said it's close to 518, right? So you can make this bigger by clicking on it. Can you see in all the direction? Can you see? Or even down. So you can use it to adjust your grid box to the size of the active site. So you have to make sure you check it and make sure that the grid box, because if you are creating the grid box here, by the time we are docking, the docking is not going to bind any other place. It's going to bind within this box. So you have to make sure that your box covers the active site. So what technically what I'm doing is I create that box around here. So my docking should be done around here. That's what I'm doing on that software. So once you do that, another thing that it can give to you next time that you can take note of is giving me the coordinate of that box. So next time when you want to do this work with maybe another set of compound, or you want to repeat it, instead of you finding this grid box, it already gives you the value here. Can you see it here? So X is this, Y is this, Z is this, dimension is this. If you want to reset it, you can click reset. Can you see it adjusts it back for me? So I can reset it again. So you can adjust your box. Let me see if so let's assume this is yeah. So this is, we have set the box around the active site, this side. Right. So let's go back. So everything is done. You can take note of these values in case you want to do next time. So you just have to set it accurately as it is. So once that is done, our work is what? Is done. So the next thing is to tell the software to what? Start. Forward. Just click on the forward. Click on it. Can you see? It's doing the docking one by one. One by one. And it's going to give us the results. Can you see? It's docking it one by one. So the aspirin is done. So it's working on chloroquine is running now. So it's done. It's now Tylenol. Tylenol is what? It's running now. So if you have 20 of those compounds, you can go and you can just on 1,000, just do that and go and sit down. So after it finishes working, it gives us the result. So it gives you the result in form of the binding affinity, the mode, the RMSD lower bound, and the RMSD upper bound. The one that is most interesting is the binding affinity. So what that is telling you is, let me try to. What that is telling you is telling you the comfort. So for aspirin, it's telling us if you count aspirin that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. It says aspirin can bind to H2 at this site in 9 possible ways. So if I click on this now, you will see this is changing, right? Can you see it's changing? So it can bind with this orientation or bind. So if it binds with this orientation, the binding affinity is what? Minus 5.3. If it binds in this, is minus 5.0. If it binds with this, is minus 5, minus 5.0. Can you see? So in docking score, to know which one is binding better, is going to be which one is giving you a more negative value. So if you look for aspirin, the maximum value for aspirin is minus what? Minus 5.3. For cleoquinion, is minus 5.8. For Tylenol, is minus 4.8. So if I ask you which one is likely to bind to H2, for instance, you can tell me that cleoquinion is having the highest binding conformation, right? So now, if you have 1,000 drugs, how do we know which one to work with? What we do most of the time is we always have what is called a reference drug. So as you do this, you can look for what is FDA approved. What is FDA approved? Excuse me, please. What is FDA approved inhibitor of H2? So we can use that as what? As our reference. So let's assume there is an FDA approved inhibitor of H2 called drug B. And if drug B is giving us minus 5.0, so If that is our reference drug, then we can say, oh, great. Tylenol is minus 5.3. It is above our reference drug. So Tylenol is likely to bind to this drug. Chloroquine is also minus 5.8, higher than our reference drug, which give us minus 5.0. So chloroquine can also bind. What about Tylenol? Tylenol is 5.0, is giving us 5.0. It can also bind. But if any drug that is below the docking binding affinity of our reference drug, you may decide not to work with it further, right? So that is that. So I'm going to stop here before we continue the second part next week. So that's second part is going to be November 1st. But I purposely give you this so that you can practice this before we meet November 1st. At least you have a whole 2 weeks to practice, to try this before we meet next week. Any question, any point that is not clear to us?
No questions from me, Dr. Doro.
Okay. I know you have done this in the past. So
Yes.
it's really familiar territory. Okay. Any Jadifi, Alia?
No, nothing for me.
Okay. So I'm going to upload this video as soon as possible so that you guys can watch it for
Dr. Doro, did you upload the one Dr. from last week, the one Dr. Scott's taught?
I think I omitted that. Thank you for reminding me. I will look for that,
Okay.
the link. I will do the two together.
Okay,
Yeah,
that
I will
works.
make
Thank
sure that
you.
I upload the two together before the end of today.
Okay,
One thing
thank
is
you.
most of the time is after some minutes or hours before Zoom send you the link. So I'm like, I think I forgot most of the time. Okay. All right. Any question, Dr. Scott? Anything that is not clear? If anything is not clear to you guys, please feel free to contact me and Dr. Scott. Feel free to contact me and Dr. Scott. Then we can assist you with that. All right. Enjoy your semester and semester
Good
midterm.
luck on your midterms.
Yeah. And probably practice this before we meet next time, because this is just part 1. Part B of it has to continue. But you can't understand part B if you don't understand part 1. Right. All right. Thank you so much, guys. If you have any question, if you are planning to go to that program I mentioned earlier, let Dr. Scott and I know so that we can factor you in and we can start planning for the traveling procedure, flight and accommodation and the rest. So
Yeah, the sooner the better.
yeah, the sooner the better. Thank you. So I think, Alia, can you send it to your group now that our meeting is going to be 4 p.m. starting from November 1st. 4 p.m. because of some that had class at this present time that we meet. All right. Bye-bye, guys. Enjoy your weekend.
Thank you. Bye. Have a great weekend.
And you
Bye,
too.
guys.
Bye.